So we are Team 8, and our project is All That Jazz, jazz reharmonization using LSTM networks. I'm Jeremiah Gelb, and I'm joined by Michael Bash. So our motivation is the harmony of jazz can be really overwhelming, but a lot of people are interested in it. This YouTube video by Adam Neely has over 1 million views, but a lot of people are very intimidated by jazz harmony. So our objective is to create a neural network capable of reharmonizing music in a jazz style. Some prior art, we were inspired by this paper, Text-Based LSTM Networks for Automatic Music Composition. They used a character-based LSTM that analyzed jazz songs sort of as like a paragraph made up of words, which were made up of characters. So they went through an entire song and tried to generate plausible songs like you would generate plausible English text. There were some limitations to this. One was real songs tend to repeat the same chord over and over again. The network picked up on that and really liked generating songs that was the same chord over and over and over again. Second of all, another limitation, viewing songs character by character forces you to learn a lot of things that are intrinsic about the chord structure. For instance, the word major and minor both start with M, but they're fundamentally different. So we address both of these limitations of the prior work with our data pre-processing step.
For source of data, we used a collection of jazz standards that was originally in the format of XLab that's used by music arrangement software program called Band in the Box. These were converted into text by the creators of another work called the LSTM Real Book. We used 1,279 of these songs as training data.
For our pre-processing step, the LSTM Real Book had already transposed all of the songs into the key of C. So we took them in this text format where it was the root followed by the quality and switched that into a Python class where the root and the quality were both represented by integers. We combined enharmonic roots, so combining A sharp and B flat, for instance. We combined exchangeable qualities. In jazz music, saying that something is a 7 chord or a 7 chord with a 13 added, they're the same chord, and it's up to the player to choose which one of those voicings they want to use. And we also removed serial duplicate chords. So this deals with the repeated chord issue from the prior work. If there were 10 Cs in a row, we just chopped off 9 of them and just represented it as 1 C. So we took this Python object and converted it into a NumPy one-hot encoding. You can think of it as a 2D matrix where one axis is the quality and one axis is the root. Then we took that matrix and just flattened it into a one-dimensional array. And then we used a generator to generate 3 chords on one side of the target chord, 3 chords on the other. Every chord was a 192 long column, and then we used a batch size of 50.
Shown here is the model description. As mentioned, the input size 6 by 192, 2 sequential LSTM units followed by a dense layer going from 512 down to the 192 to represent the output chord prediction. Below is some information on the hyperparameters, optimizations, and loss functions that were utilized, as well as details on the number of parameters required for each layer. In justification of the model, we tried a few different model topologies, including fully connected RNN and GRU. Decided to use LSTM due to the flexibility options for additional parameters allowing advanced control, as well as its success in a variety of other similar applications. Additionally, it's less susceptible to the vanishing gradient issue that's seen by traditional RNN. Shown here are the training results, an accuracy of 0.9115, F1 score 0.912. This is for a total training steps, which was 71,680. as mentioned before, summary of the total trainable parameters of about 3.6 million against a set of data that was generated from the data generator from the training set of data did pretty well, 96%, and on sets that the model hadn't seen during training, 68% consisted of 3 songs, and this were both batches of 25.
So to go on with what Michael said, for the final comparison, we let the model see 3 songs it had not seen before. They were classified as easy, medium, and difficult in terms of harmony. The easy song was All of Me, the medium song was 4, and the difficult song was Giant Steps. The model got 7 out of 7 predictions correct on the easy song, 6 out of 9 on 4, and 4 out of 12 on Giant Steps. You can see to the right just an example of what it predicted for Giant Steps. The red lines are where the model guessed an incorrect chord as its top choice, and the green lines are where the model guessed the correct chord. Now, to compare the model with just more of a baseline, we input a 2-5-1 chord progression, which is just a very typical chord progression in jazz, and we did that in all 12 keys. Where the model got it correct, I highlighted it in green, and it did that 8 out of 12 times. And additionally, in blue, 2 out of 12 times, it got the root note correct, but not the quality correct. But interestingly enough, it guessed D minor and E minor, which would be the correct qualities in the key of C for those root notes. So probably because the model was trained in the key of C, it guessed those values. Now a demonstration of reharmonization. Here is just a simple harmonization of the song Twinkle Twinkle Little Star. Then I input the chords to Twinkle Twinkle Little Star and let the model guess at the chords in between. So basically generating transition chords between all of the original chords. And here's how that sounds. So subjectively, I think the model did a really good job at generating plausible jazz transition chords. I took the top 3 suggestions that the model had and then just used my ear to pick the chord that sounded the best with the melody. But I think it is still quite impressive that the model could harmonize a melody that it had no idea about. All it had as an input was just some chords. And here's some of the references we used.